Hey guys. Hey guys, it is the start of the bonding unit. And I'm going to introduce you guys to some of the bonds, both bonds and chemical bonds, and they come in varying strengths. Okay. First we have the covalent bond, the Pierce-Brodson bond. Probably the weakest bond. The covalent bonds are between nonmetals. It's a nonmetal and a nonmetal. And they share electrons. We're going to get into this a little bit more probably tomorrow. So an example of a covalent bond are molecular compounds like methane, molecular compounds like water, or even diatomic elements like oxygen, chlorine, sulfur. Nonmetals bonded to other nonmetals. That's a covalent bond. These are weak. Now, I don't mean to poke fun at my main man, Pierce-Brodson, but he's probably the weakest of all of the bonds, for sure. Good bond, lots of great movies. His last one was terrible. You can YouTube. Actually, I'll put the clip in the link today of him. He's like, what is it called? Parasurfing down a glacier or something? Is ridiculous. Terrible CGI. Okay. Next type of bond is an ionic bond. And here we have Sean Connery, one of the first bonds in a very inappropriate picture here that you guys get to see. An ionic bond is where the metal takes the electron. There is unequal sharing. Because they taken, right? Bond, James Bond. How do you like your martini? Taken, not stirred. Okay, so it's unequal sharing. An example is like sodium chloride. And what you get is one of the atoms, and we'll talk about it later in the unit, takes all the electrons, leaving it very negative. And because the other one lost its electron, it's very positive. And there is, that dropped. And there is attraction. Ooh. Brown chicken, brown cow. Okay. Then we have metallic bonds. Oh, it looks like this guy. Look. Hey, time to work out. Not that much, not that much, not that much. Okay, right there. Okay. So we have this guy. Oh, what's his name again? Daniel Craig. So Daniel Craig is the metallic bond. Definitely the beefiest and most muscular of all of the bonds. It's a strong bond. It's metals only. And basically you have a positive ion and a sea of electrons. So we have shirtless Daniel Craig here. He's positive, and then surrounding him, because he's just so darn attractive, are all of these electrons. Now, funny story about this picture. Many years ago, I was Googling different bonds to show, and I searched for Daniel Craig when this movie came out. I forget the name of this James Bond movie. And it was an image search. And I guess this is an iconic shot where he's coming out of the water all super buff. And I'd left my smartboard on. So my smartboard had image search, like all of the little thumbnails of shirtless Daniel Craig. And my phone rang. So I was talking on the phone. I was oblivious to all of this. And one of the vice principals walked in. He's like, "What are you doing? What's going on right here?" And I was on the phone. I was like, "Excuse me." So I was like, "I'm researching bonds to show the kids." And it was super awkward because he's like, and then I saw what was happening. I was like, Nothing wrong with shirtless Daniel Craig. It's just an awkward story. Okay. So today I'm going to talk about the octet rule and blow your mind. Absolutely blow your mind. You will love the octet rule once I'm done talking to you about it. To talk about the octet rule, we have to go back to Bohr diagrams. Do you remember Bohr diagrams from the start of the year? So chlorine has 17 protons because it's element 17, and its mass number is 35, so it's got about 18 neutrons. Maybe some of you remember doing this. It's got 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the third shell. So from Science 10 and the very start of Chem 20, maybe you went over this. I know we did in IB. The very last shell is called the octet. No, it's called the valence. And we're only going to be dealing with the atoms that fill the octet to 8 electrons. And what the octet rule deals with is the very last shell. All of the other stuff doesn't apply because it doesn't really affect electron sharing for right now. We're only concerned with valence because valence deals with sharing and bonding. Okay, these other shells are full. This shell is full. So it's as if we don't worry about it. Now, we're going to talk about protons and their attraction a little later, but not today. Now, here's where your mind's going to get blown. Lewis diagrams are the next type of diagram that use the octet rule. And the way Lewis diagrams work is like this. Lewis diagrams show the electrons around an atom, but only the valence. And you have to think of an atom like that chlorine, that Cl right here. You can't see me pointing. Okay, the Cl right here, that it's in 3D. There's electrons that are all around it. And that's kind of tough when it's flat, like 2D. So we are only going to be dealing with atoms that have a maximum of 8 electrons in their Lewis diagram. So there are drawings that will have more, that's true. With the IBs at the end of the year, if there's time, I might get into a bit of it. But we're only going to be dealing with 8 electrons per atom. And you could have less than 8. Now, those electrons are put into 4 quadrants or quote-unquote orbitals where the electrons sit. Now, the IBs know why you can only put 2 into every orbital, because electrons, because of something called the Aufbau principle, have an up and down spin. Maybe the IBs remember that from the start of the year, but you can only have 2 electrons together. You can't have more than 2 in a pair, and if there are, they move to another orbital. So, what does the Lewis diagram look like for chlorine? Well, chlorine, as we just said on the last page, has 7 valence electrons. So what you would do, I'm going to use the little boxes here, is you'd put 7 electrons around the chlorine. However, you have to fill each box one by one. Once they're all full, you can start doubling up an electron. So here's what that looks like. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. You can start anywhere and you can go clockwise or counterclockwise, but you can't overload one orbital until all orbits have 1 electron. So it would be wrong. You might actually get the same picture, but it would be wrong to do it like this. 1, 2, 3, 4, 5, 6, 7. It's a fluke that you're right doing it that way. Okay? So you got to go clockwise or counterclockwise. You also can't do this kind of thing. 1, 2, 3, 4, 5, 6, 7. No. Bad student. You can't do it that way. Now, these boxes, you don't have to put the boxes around there. In fact, after this slide, I'm never going to show the boxes again. That's just to remind you that electrons are spinning up and down in each of these orbitals. And we show an electron as a dot. It's not the best way to show something very complicated. That's basically a packet of energy that's neither a wave nor a particle, but this is where we're at. Okay. Now, the IB students, you might be remembering SPD rules and be so glad we don't have to worry about SPD hybridization. We're not doing that right now. We're just going to be dealing with Lewis diagrams. Okay. So yes, we had to use quantum chemistry in IB, but we don't need to worry about that because physics doesn't work very well explaining very complicated things simply. Okay. So if you're like, what is happening? Don't worry, 8 electrons. Okay, now let's go over some terms and terminology. Electrons that are paired are called lone pairs. Lone pairs are a happy couple, and they do not usually partake in bonding. They just don't. They're stable. They're happy. Single electrons, however, are bonding electrons. Bonding electrons are desperate for companionship. They are looking for other single electrons. Maybe they're on Tinder for electrons and they're just looking to swipe left, I don't know what it is, left or right, when they see a single electron. Oh, you're a proton, ew, gross. So they're always on the lookout for another electron because they want to be stable. This electron is jealously looking at this couple grow old together, and this single electron is wondering what it's doing with its life. Okay? Sorry, you'll find love. You guys are very young listening to this. There's somebody in the world for you. And if not, that's okay. Maybe they'll be robots. All right. So let's say we had sodium and nitrogen. What would the Lewis diagram look like for sodium? Now, you'd have to do the Bohr diagram, and that's a pain in the butt. So I'm going to teach you a shortcut to figure out how many valence electrons each element has. Group 1, hydrogen, lithium, sodium, has 1 valence electron because it's in group 1. Group 2, that's beryllium and magnesium, has 2. Skip a few. Skip all the middle until you get to boron, and we're going to call that group 3. Then we have carbon. That's group 4. Then we have nitrogen. That's group 5. Okay, I screwed up the periodic table. I made it too chunky right here. One sec. Okay, there we go. Okay, then we have oxygen, then we have fluorine, and then we have the noble gases, which have 8, except for neon. So it goes 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So how many valence electrons does sodium have? Well, you could do the Bohr diagram, 11 protons. Okay, we got 2 in the first, and 8 in the second, and we got there one valence electron, and no, why don't you just do 1? Okay, where does it go? Who cares? It's got 1 valence electron. Why is sodium so reactive? I'm going to blow your mind. It has no stability and 1 very desperate electron that is craving some kind of relationship. I don't know why. Maybe it had a rough childhood. Its biological clock could be ticking. We don't know, but it really wants companionship. Now, nitrogen, again, you could do the Bohr diagram with 7 protons, or you could use my super fast cheaty system where you go 1, 2, skip a few, 3, 4, 5. Nitrogen is in group 5. It's actually in group 15, but when you subtract 10, you get 5. So that's another way you can do it too. So we have to put 5 electrons around nitrogen. 1, a 2, a 3, a 4, a 5. Pow! So nitrogen has 1 lone pair and 3 bonding electrons. So single nitrogen is pretty reactive. It does not like to be single. It likes to bond to other stuff. Okay. Now, we are going to get to building compounds, but you build compounds by circling single electrons. So, for example, hydrogen looks like this. So it's got one electron. That's all it can do. And another hydrogen electron. Okay, oxygen is in group, what is it? Let's draw the little thing out here. Okay, 1, 2, skip a few, 3, 4, 5, 6, 7, 6. Right? Oxygen's in group 6. So it's got 6 electrons. 1, 2, 3, 4, 5, 6. So why does water look like H2O? Why are there 2 hydrogens for every oxygen? Because remember, molecular compounds aren't connected with charges. It's a coincidence that water kind of works out that way. It works out that way because this single electron here sees this single electron here. And it's like, ooh, la, la. This one sees this electron here. And it says, how you doing? That's Joey Tribbiani from Friends. Okay, so those electrons smush together, and you get this electron from there. Now I'm going to show X's as the oxygen electrons. So the hydrogen and the oxygen make a bond pair, which acts like a lone pair. So that's why it exists that way. Pretty cool, right? That is going to be the lesson for tomorrow, is now we're going to be making more complicated compounds by connecting the dots. That's literally all this is glorified connect the dots.